So, for your two topics for this week in 172, they are complex numbers and then parametric equations. The really convenient news, I suppose, if we would consider it news, is that there's a whole lot of prerequisite stuff related to both of these topics, which will hopefully make the topics themselves make a little bit more sense or maybe click a little quicker or anything related to that when you're actually working through the new material for the week. So, complex numbers, you at least saw those back in 171 when you were looking at things like 3 plus 4i. Right, a complex number has what's called a real part and an imaginary part. And we're going to work with that for this week in 172 as well. But what we'll actually be doing is working with complex numbers in rectangular form and also working with complex numbers in polar form. Polar form is the one that I just wrote here at the bottom of the screen. And again, the good news, if news is what this actually is that a lot of the stuff we'll be doing when converting back and forth between the two is exactly the same kinds of things you did last week with ordered pairs in polar form or polar coordinates and polar equations. So we'll get to that in just a second, but what we'll start with is a review from 171 type material, just on adding, subtracting, multiplying, and dividing complex numbers. So let's say we have a complex number 3 plus 4i, and we have another one, 8 minus 12i. We can add, subtract, multiply, and divide both of those numbers. If we want to add them, what we would do is add 3 plus 4i to 8 minus 12i. And to add complex numbers, we'll add the real parts. 8 plus 3 is 11. We'll add the imaginary parts. 4 minus 12 is negative 8i. So adding complex numbers is essentially combining like terms, combining the real parts and then combining the imaginary parts. To subtract them is actually the exact same process except using subtraction. Z1 minus Z2 would be 3 plus 4i minus 8 minus 12i. We'll subtract the real parts. 3 minus 8 is negative 5. And 4 minus negative 12, that's really plus 12. So it's plus 16i. To multiply Z1 times Z2, that would be 3 plus 4i times 8 minus 12i. But to multiply something like this, we should FOIL. 3 times 8 is 24. 3 times negative 12 is negative 36i. 4 times 8 is 32i. And 4 times negative 12 is negative 48i squared. There's several things we can do to simplify this. We can combine like terms in the middle. Negative 36 plus 32 is negative 4. And remember, thinking way back to 171, I squared is equal to negative 1. So really what we've got there at the end is negative 48 times negative 1, which is really positive or plus 48. And 48 plus 24, we can combine those to get 72. So a fair bit of more work to simplify these or simplify multiplication, more work than just adding or subtracting. But at the end of the day, the essence of what we're doing is foiling. So, which is something that you have at least done a lot in the past as well, I'm sure. The last operation to review is division. Z1 divided by Z2 is actually not really anything to do. Z1 over Z2 is just that. Z1 on top of Z2. So after multiplying and all the additional work there, a little bit of a break for division because there is no work. But questions about adding, subtracting, multiplying, or dividing those complex numbers. How it works, what we did, why we did it, anything like that. Okay. So, your task for the week, kind of your goal, is to ultimately be able to multiply and divide complex numbers in polar form. So that conversation will have to happen specifically in 172 class, but what we can talk about is converting back and forth between rectangular form and polar form of a complex number. That's also one of your tasks for the week. But thankfully, the skills for doing that are exactly like what you looked at last week. Last week you had polar points and using polar coordinates. You had points using rectangular coordinates, and you could convert back and forth between the two using a specific set of equations. That's literally the exact same process we're going to look at today, and it's the exact same equations that you'll be using to make these conversions for this week as well. So let's say that we have the complex number. Let's do the 8 minus 12i one. That's an x value paired with a y value. 8 complex numbers in rectangular form are written. They're in the form of z equals x plus yi. What we do to turn that into something in the form of r cosine theta plus I sine theta is to turn x and y, or is to use x and y to calculate r and theta. The equations you saw last week in order to make that exact calculation, the equations were r squared equals x squared plus y squared, which essentially means r is equal to the square root of x squared plus y squared. But then tangent theta is y over x. So literally those exact two equations from last week are exactly what we'll use this week too.
I have a, I have a question.
Yes.
So I was writing as you was talking, so you may have said this, but where it has z equals r cosine theta plus I sine theta. So the r is the I in that. Like, is there not an r there for that y?
For the y? What do you mean? Huh?
Oh wait, because y is equal to sine theta. Is that I'm missing.
No. Eventually y is going to be equal to r sine theta. I don't know if that's what you're asking me.
So the x and y that you got underneath the 8 and the 12, you said I'm gonna rewrite this as, the next equation. So the z equals the r cosine theta.
Yeah.
That represents the x.
Yeah. It represents, yeah, that's a fine way to say that. Yes, I agree.
Okay.
True.
All right. Okay, go ahead.
Okay. So our goal is to take this 8 minus 12i and somehow figure out how to rewrite it so that it looks like this, what I just circled there in red. How we'll do it is by using x and y in these two equations in blue. So for that conversion, we need to figure out an r value and a theta value. To figure out r, it's literally the square root of x squared plus y squared. That's the square root of 64 plus 144. And that simplifies into 4 times the square root of 13. So our z value, or sorry, our r value is 4 times the square root of 13. To get theta, we'll use inverse tangent, since tangent theta equals y over x. Inverse tangent of y over x. We'll use that to figure out theta. I'm going to do this in degree mode. Normally, the default is going to be radians, but degrees, I mean, you can absolutely see these in degrees as well. And doing it in degrees, at least at the moment, will make it a little easier for our conversation. So inverse tangent negative 12 over 8 is 56.31 degrees. Okay, so what's going on? Think of that x and y value. Think of it like an ordered pair. I mean, you'll hear a little bit more to this story throughout the week when you're actually in 172. But for the moment, let's just think of it like an x value with a y value. 8 units to the right, negative 12 units down would put the point, if we were to think of it like an ordered pair x and y, would put the point there in quadrant 4. What we've just found is that the angle here is 56.31 degrees. What we want is the angle in standard position. Now, we're always interested in angles in standard position. What we can do to get that angle is to use 360 minus 56.31. So the angle in standard position that we need is 303.69 degrees. And so that tells us everything we need. We have r, we have theta. So r is 4 times the square root of 13. And then cosine theta plus I sine theta. And I'll scoot all this back over in just a second. Make it a little smaller. But to make the conversion from something that's in rectangular form to something in polar form, we need to find r, we need to find theta. Using the two equations above in blue is how we would do that once we get them. Just plugging them in to their proper spots is what is it to wrap that up. Questions about anything we did there? Okay, let's say, so we can go the other direction as well. Instead of, so we just went from rectangular to polar. If we want to go from something in polar form, to something in rectangular form, we need to use the r value and the theta to figure out x and y. Well, again, the same equations from last week. X is equal to r cosine theta. Y is equal to r sine theta. And so literally we'll take each of those equations and apply them with our r and our theta value here to figure out x and y. So x equals 6 cosine pi over 3. Y equals 6 sine pi over 3. Cosine at pi over 3 is a half. Sine at pi over 3 is the square root of 3 over 2. And so our x value and our y value, 6 times a half is 3. 6 times the square root of 3 over 2 is 3 times the square root of 3. So to convert from polar form to rectangular form, we've got the x and y now. We just need to write it 3 plus 3i times the square root of 3. So I'm going to quit sharing my screen for just a second. I think the folks who just came in, I think y'all probably cannot see my screen. So I'm going to quit sharing for everyone for a second and then reshare it right now. But any questions about that conversion? We're going to do one more next to go from rectangular to polar again. Typically that one is a little trickier of a conversion to do. Questions about either of these two first? Okay, so let's do one more from rectangular to polar. Let's say we have 6, let's do this one, -6 plus 8i. And we need to convert this into this complex number. We need to write it in polar form. We need to get r, which means to figure out r and theta. So take x and y and figure out r and theta. R, it's the square root of x squared plus y squared. That is the square root of 100, which is 10. So our r value is 10. To get theta, we'll use inverse tangent of y over x. That's approximately negative 53.13 degrees. But the point, if we were to use the x and y values to plot a point, we would get -6, 8, which is a point located in quadrant 2. So we need an angle in standard position that corresponds to that point. What we just found out from this inverse tangent function is the angle here, and that it is 53.13 degrees. The angle in standard position then, theta, is 180 degrees minus 53.13 degrees, which is 126.87 degrees. So our complex number is 10 cosine theta plus I sine theta.
So even though we got a negative as that theta, we still put it in whichever quadrant the points are in, and that's the angle that we use to figure out. Okay.
But you're using it for the reference angle.
Okay.
And the reference angle is always the one connecting to the x-axis.
Okay.
So if you get a negative number back here, I mean, you can we're essentially ignoring the negative sign and just using the 53-degree part, which is exactly what we did above as well. I'll scroll back up in a second, but well, I don't think I can squeeze it all in. But that's exactly what we did back here as well. For the first one, we ignored the negative sign only because we were interested in the reference angle. And again, that's the one connecting the x-axis and the angle, the line we drew. So the reference angle is the one here in the between there. Other questions about any of those things? Because our next task, we're going to switch gears and talk about the second topic for the week, which is parametric equations. Okay, so parametric equations, what they are it's a pair of equations that are defined in terms of some other parameter, a variable, but some other parameter, and usually that parameter is going to be the letter t. So x is equal to 2t plus 5, y is equal to t minus 6. This is a pair of parametric equations. We have an x value and a y value, both defined in terms of some other thing, some other variable, which literally is what parametric equations are. So one thing we can do with parametric equations, and this will be one of your tasks for the week, is to create a graph. Well, we can create graphs of equations by plotting points. That's always an option you have. It's not necessarily always the best option or the quickest or the most efficient, but it's at least always an option. And it is an option this week, and it's probably one of the better options, if not the best option, for these graphs. How we would create a table of values here is we would pick values for t. And use those to calculate the corresponding x and y values. We calculate the corresponding values the same way we would calculate corresponding values at any other point. We plug in -2 for t and calculate x. Plugging in -2 gives us -4 plus 5, which is 1. Plugging in -1 gives us -2 plus 5, which is 3. 0 plus 5 is 5. 2 plus 5 is 7, and 4 plus 5 is 9. Repeat exactly that process to get the y values. -2 minus 6 is -8. -1 minus 6 is -7. 0 minus 6 is -6. And then we get -5 and -4. But what we've got, though, is a series of ordered pairs, an x value with a y value, that we can plot to create a graph. (1, -8, 3, -7, 5, -6, 7, -5, and 9, -4. We can connect the dots to generate the graph. So, I mean, this isn't an intricate graph. I mean, this is a linear graph. So not quite like the graphs you saw last week, the polar graphs, where they were all sorts of, maybe intricate shapes. These are going to be the more typical kinds of graphs you've seen: linear, quadratic, square roots, maybe, those kinds of graphs, though. Depending on the types of parametric equations you have, you could maybe see something like a circle, but frequently they're going to be the more typical graphs that you've encountered a lot more in past, in 171 maybe. But the whole point of this is that to create the graphs, we can absolutely use a table of values. That's a really common approach. We've looked at it a couple of times if you've attended those bootcamp sessions with us this semester, but whoops, I didn't mean to do that. The question's about how we got the graph. Okay. So in addition to creating the graph, another task you'll have for the week is to eliminate the parameter in these two equations. So what that means is that somehow we need to take these two equations, x equals 2t plus 5, y equals t minus 6, and merge them together in order to create a single equation that involves just x and y. How we will do that is by using by going back to a topic from 171, solving systems of equations. And one of the ways you solved systems of equations back in 171 was using the substitution method. We will use exactly that process to eliminate the parameter here. So I've just put in the chat a series of steps, 4 steps that you can use for eliminating the parameter, for solving a system of equations using substitution. We're going to use exactly those steps, though, to eliminate the parameter here. So let's practice that. We'll do a couple of these, several of these. So x equals 2t minus 5 and y equals t minus 6. Step 1 says we need to pick one of these equations and solve for one of its variables. Well, what we'll be solving for, we're always going to solve one of the equations for t. So we can either solve the x equation for t, or we could solve the y equation for t. Just notice that if we solve the x equation for t, we're going to create fractions. Right? At some point, we're going to have to divide by 2, which is going to create fractions. Which it'd be nice to avoid that if we can. And as it turns out, I'm actually going to turn my phone on silent so it doesn't keep ringing. Okay. As it turns out, solving the y equation will allow us to avoid fractions, because to solve the y equation for t, all we've got to do is add 6 to both sides, and that tells us that y plus 6 is equal to t. So no fractions, just a single step, and boom, we got it. What we do with that, how substitution works, is once we've solved for that variable, we take the expression it's equal to and plug it in place of t in the other equation. In this case, that gives us x equals 2 times y plus 6 minus 5. So literally, we have accomplished our task. We took the x equation, we took the y equation, merged them together. Now we have a single equation that involves just x and y. We're going to simplify it a little bit. We're going to make it look a little better, but we have created that single equation. To make this look a little better, we can distribute the 2 and then combine like terms. 12 minus 5 is 7. Questions about anything we did there? Solve one equation for t. It literally doesn't make a difference. It just could be that one equation is a little simpler to solve than the other. But pick an equation, solve it for t, plug that expression into the other equation in place of t, and then simplify. So I'll scoot that up. Let's look at another one. X equals t minus 5. Y equals 2t plus 1. We just did 2. Let's do 3. 3t plus 1. So to eliminate the parameter here, pick an equation and solve it for t. That's step 1. So between the x equation and the y equation, the x one would be just a little simpler to use. If we want to solve that for t, we just need to add 5 to both sides. And then once we've got that expression, we'll plug it in place of t in the other equation. Y equals 3t plus 1, and then simplify. To simplify, we'll distribute the 3, and then combine like terms. 15 and 1 gives us 16. Questions about that one? Okay. Let's look at one more of these. Let's say x equals 4t minus 1 and y equals t squared. So, same task, eliminate the parameter, same process, use substitution. With one additional thing I'm going to point out, anytime one of the equations has an exponent, if you can avoid solving that equation for t, it'll be better. You're not obligated to, it's not an imperative thing, but it would be better. So, that said, I'm going to solve the x equation for t. 2 steps for that. First, we'll add 1 to both sides, and then we'll divide everything by 4. That tells us that t equals x plus 1 over 4. Once we've got that, we'll plug it in place of t in the second equation to get y equals x plus 1 over 4 squared. This is a perfectly reasonable way to leave the answer. As you work through the material this week when you're in class or whatever, it'll be shared. It may be shared. If you're in my class, it'll be shared. Some folks just have different preferences on this. It's a really common preference for to square the top and bottom separately, right? So anytime we're squaring a fraction, that's the same thing as squaring the top and bottom separately. So generally, a lot of times folks will request for you to write the answer, leave the answer like what's down here. So for that reason, I will square the top and bottom separately and leave my answer that way. questions about that one? Okay. I'm going to put another screenshot in the chat. What we really frequently use these parametric equations for is to model some sort of a word problem. And so I put a screenshot in the chat of a word problem. We'll go through it. We'll work through every piece of this together in just a second. Before we do that, I'll give you a moment to read through the question, and then we'll talk through everything together. So what's going on is that a ball has been thrown through the air, it has this initial velocity, it has the angle that it was thrown at, but ultimately we're given this pair of parametric equations that model the position of the ball. So this x equation models the ball's horizontal distance. It's in feet. The y equation models the ball's vertical height. But that's what x and y do anyway, right? I mean, I'm not necessarily sharing anything new. X is always horizontal, y is always vertical. That continues to be part of the story here too, though. So we have this ball. If we were to create a graph, I'm just going to make a really basic sketch, but if we were to create the graph by getting a table of values, it would look something like this. It would be a parabola. And so we have this series of questions, 2, 4, 6 questions underneath we can answer by using actually skills that you learned before getting into 172. We're not actually going to talk about anything specific to 172 when we go through these 6 questions, or these 6 parts. So for part A, the question asks, how high is the ball when it's thrown? Anytime you're talking about a height, that sends you see the word height, that's the key word, says go use the y equation. In order to calculate anything about the y equation, we need to use the time, right? A t value. T stands for time in seconds. So we need to calculate y when t is 0. Anytime you see the word initial, that means when time is 0. The initial height, the initial revenue, depending on the context. But initial whatever always means time is 0 and calculate something using that. Since we're after a height, we should calculate y when t is 0. So to do that, we'll plug in 0 for t. That's negative 16 times 0 squared plus 29.39 times 0 plus 6. 0 plus 0 plus 6 gives us a height of 6 feet. So when the person threw the ball, it was released at a height of 6 feet in the air. So on the graph, that's essentially telling us that the y-intercept is 6. B is about the same question. B asks, what is the height after 1 second? Or after 0.1 seconds. What that's requesting from us is, again, to calculate y when t is 0.1. So the exact same question, just we have a different time now, but it definitely works the same way. Negative 16 times 0.1 squared plus 29.39 times 0.1 plus 6. This we can use in the calculator. 16 times 0.1 squared. Sorry, negative 16 times 0.1 squared plus 29.39 times 0.1 and then plus 6. Putting it in the calculator, we get 8.78 feet. So the ball after 0.1 seconds, it's 8.78 feet above the ground. Questions though about A or B? Similar questions, that's why I did them kind of so quickly back to back, but questions about either of them. We're given a time value, plug it in to calculate a height. And again, height, always a keyword meaning to use the y equation. Distance, always a keyword meaning to use the x equation, horizontal distance. Part C then, the third part here, what is the ball's maximum height? Maximum height. Two keywords, height sends us to the y equation. Maximum specifically tells us to find the vertex. Right? That was a keyword back in 171 as well. So what we're being asked for here is the height of the ball at its vertex. In order to find the vertex, there's two components to the vertex. Using the y equation, there's a t value. There's a time that the maximum is reached. So there's a time when the maximum occurs, and then there's a specific height associated with it. To calculate the height, though, we have to figure out t first, right? That's how the y equation works. The y equation says, oh, do you want to calculate y? Great. Plug in a t value to make it happen. So we cannot calculate the height until we know the time when the maximum occurs. But thankfully, going way back to 171, we have a really quick way to figure out the time for the maximum. Negative b over 2a. Probably used that a lot back in 171 when you were in the quadratic section. Negative b over 2a tells us that the maximum occurs, or the vertex occurs, at 0.92 seconds. So not so much, the time is not the answer, right? The times, we need the time, but the answer to the question is the maximum height. And so to get the height, we'll plug in 0.92 in place of t. This, at this point, can go straight into the calculator. Negative 16 times 0.92 squared plus 29.39 times 0.92 plus 6. That gives us 19.50 feet. Questions about C? D asks, how far has the ball traveled when it reaches its height? So D is asking, so, a person is standing here, they throw the ball and eventually it makes it this far. How far has it traveled when at that point? That means we need to use the x equation. Just like the t equation, though, the x equation, or sorry, just like the y equation, the x equation requires a t value as well. Specifically this time, we want to know x when t is 0.92. Right? The maximum height occurs after 0.92 seconds. We know what the maximum height is, but now we need to know how far away from the person the ball is at that point. So we'll use x and plug in the time we already know. So 40.45 times t says that the ball is 37.21 feet away from the person who threw it. Questions about D? Okay. E asks how long is the ball in the air? Well, I'm going to go back up to the graph. The ball is in the air from the moment it's thrown until it reaches the ground. When the ball reaches the ground, its height is 0. So, how long is the ball in the air? What that's asking us to do, so talking about height, that means y. We should use the y equation to solve for t. Right? How long means find t. We use the height equation to find the time when the height is 0. So we'll set the y equation equal to 0. And now we can solve for t. Right? Y represents height, so put a 0 there. Then we can calculate t. To solve it, this is a quadratic equation. To solve a quadratic equation, we have two options. The two options we have are factoring or using the quadratic formula. We can't factor this isn't going to factor, but we can use the quadratic formula. That's negative b plus or minus the square root of b squared minus 4ac over 2a. In our case, that's negative 29.39 plus or minus 29.39 squared minus 4 times negative 16 times 6 all over 2 times negative 16. So I'll calculate that square root part now, 29.39 squared minus 4 times 16 times 6 is 35.32, approximately. So what we've got here, though, we're going to get two answers. Negative 29.39 plus 35.32 divided by negative 32. That gives us negative 0.19 seconds. If we use the minus part, we get 2.02 seconds. Since we're talking about a time or the time the ball reaches the ground, the negative answer doesn't really make sense. I'm going to put an X over, not because not because we've done anything wrong or the answer is actually the answer, or it is the solution. It's just a negative time, which doesn't make sense. So anytime you're talking about time or asked about a time, you need to, if you happen to get a negative one, that one's not going to be the answer. We've got to exclude that. And it's really common for these to get a positive time and a negative time. So just be on the lookout for that. Questions about anything we did for E? So we have one part of this left, and that's F. Whoops, and not in red. How far does the ball travel when it reaches the ground? So I'm going to go back up to the graph for a second. So we know when it reaches the ground, it's going to take 2.02 seconds. But what we'd like to figure out is how far that distance is, or what that distance is. That means we need the x value, but we know the time we're using. We want to know the x when t is 2.02 seconds. So the x equation is a little more straightforward than the y. It's at least linear. So to calculate x, we'll plug in 2.02 for t. That's a calculation. 40.45 times 2.02 tells us that the ball is approximately 81.71 feet away. Questions about that one? Or questions about anything else? So like always, it's the intent for the stuff I've got planned to take about an hour. We're right at the hour mark. That leaves us, my hope is that leaves us 30 minutes for questions that you've got about anything you're working on. So we're at that point. I put a second survey link, the second survey link in the chat. If you could complete that soon now, that would be great. There's the same two questions you answered at the beginning of our time. It's really quick. I think the average response time on the first one was 6 seconds. So before you leave, though, if you would complete the survey, that would be great. I know I ask you to do a lot of surveys. If you've been here for all of the weeks, you've done a lot of surveys, and I do appreciate it. They are important. They do matter. I want to make that clear. I try to say this every week, but some weeks I forget. But your feedback does matter. It does get used. It gets looked at. It impacts what happens week after week. So thank you for completing them. I appreciate you completing them. But do please complete this one before you leave, of course. But for the rest of our time together, I will so gladly answer any questions you have about anything you're working on. Could be about anything from today. Could be about anything else whatsoever related to the class. Feel free to stay as long as you want. If you don't have questions, I know it's a test week. If you have study plans or whatever related to that, stay as long as you want. Feel free to leave when you get ready, but I'll be here answering questions until we're done.
I have a question about one of the websites. Oh, go ahead. Somebody saying something?
No, I mean Jackson's typing something, but you can go ahead.
Oh, so I have a question about one of the web assigned homeworks from last week. Since we have a moment, let me get to it. I didn't know this happens. So hold on.
You're welcome, Jackson. Thanks for coming. Thanks for hanging out with us.